Hey everybody, it's Mr. N here, and we are doing some optimization problems. All right, so take a look here. Steps to solve optimization problems. First of all, what are optimization problems? Well, these are problems where you're trying to maybe make the largest box for the smallest amount of money. Trying to find the shortest distance for some sort of curve. You're optimizing that distance. Things in that nature. Over here, where would you place, like in this one, you have some wire, where would you place it so that things work out, so that you are minimizing the cost, but maximizing what you do. So those are kind of like what optimization problems are. So first, make sure you read and understand the problem. Determine what are the unknowns are, what you are given, what you're going to solve for. So kind of like how we did related rates. Draw a diagram, introduce some notation, q f of x, express q of f of x and other symbols. If you have more than one variable, what's important here, try to relate them into a one variable equation. It just makes things much easier. And then you're going to try to find the absolute max or minimum. So these are the basic steps. And with optimization problems, it's almost like related rates where we just got to do them. You got to do them, and then you start understanding. The most common, the most used optimization problem is this box problem. So let's do a box problem to start off. So it says, a manufacturer wants to design an open box having a square base. Here's a key right here, something key. Open box. So that means this is open at the top. There is no lid on it. Okay? And it says, having a square base and a surface area of 108 square inches as shown. What dimensions will produce the maximum volume? Okay, so here's what I'm given. I'm given this square base. I'm given the surface area. So I know right away I need to use a surface area formula as part of this somehow. But then I want to maximize the volume. So somehow I need to relate the surface area and the volume. So let's write these formulas down. So the surface area on this, and here's all the things that we're given. I'll list all my givens again. We're given the box, and the surface area is the area of the base, and there's only one base plus all the sides. Okay, so we can express this as x by x, x squared, plus all the sides here. You have x times h, and you got 4 of them. So 4 times x times h, and this equals 108 square inches. All right? And then we have the volume, and the volume is the area of the base times the height, which would be x squared h. All right, so now I'm given x squared plus 4x h equals 108 as my surface area, and I want to try to maximize this volume. So for maximizing volume, I'm going to be taking a derivative, right? We take our derivative whenever we want to try to maximize something to find our maximum points. But I've got x squareds and an h, and I want to keep this all in terms of one variable. So I'm going to do this, and I will solve this for h. How about we solve it for h? You could do it either way, but I think h will be a little bit easier for our work right now. So if I take this equation and I solve it for h, I will get 108 minus x squared divided by 4x, and that's what h will be. So let's plug this in, and we get the volume equals x squared times 108 minus x squared all over 4x. And I'm going to clean this up a little bit. I will simplify it. So I'll end up with this reducing with one of those. I'll get 108 over 4x, which is 27x, minus I'll get x cubed over 4. So minus x cubed over 4. So here's my volume. I'm going to rewrite it up here. 27x minus x cubed over 4. Now, it's important at this point, before you try to maximize something, remember, when I want to find the absolute absolute, maximum or minimum, I need the endpoints. And what are the endpoints? Well, the endpoints are going to be the domain I'm using. Well, let's see. What values can I use for x to find out my domain? So I can use any negative values of x? No, because you can't go negative on the x. But you can go 0, right? We could say it's 0, hypothetically. So our domain, our feasible domain, and 0 won't work because if you start multiplying by 0, you're going to get a 0 volume. But hypothetically, you can. So we'll go from 0 all the way out to, well, how far out can I make my x? That means I want to take my 27x minus x cubed over 4, and I want to find out at what values will x be greater than or equal to 0, is what I want to know. So I can set this equal to 0 and solve it, and I will get x, I could take that out, and I get 27 minus x squared over 4 equals 0. So we know we have x equals 0. That's part of my domain. And then this 27 minus x squared over 4 equaling 0, right? If I bring the x over, multiply by 4, I get 108 equals x squared. X is going to be the square root of 108. All right, so that's my domain. I can go all the way out to the square root of 108. So I found where x would be 0, and I want it to be greater than that, or in between that, right? If I go less than 0, it doesn't work. If I go greater than the square root of 108, I get a negative value for x. It doesn't work. So I have to keep it bounded in there. Then I take my derivative at this point because I want to maximize something. So I will take my derivative. I will get my critical points, and then I got to test those and the endpoints to see what gives me the maximum. So let's take the derivative at this point, and I will be taking the derivative of this. So I'll write it as v prime. You can write it as dv over dx. It doesn't matter either way. And I will get 27 minus, this is 1/4 x cubed, so it'll be 3/4 x squared. Okay, set it equal to 0 and get your critical points. Solve this for your critical points. I'm running out of room, so I'm not going to show too much work here, but you'll get here 3x squared equals 108, right, when you set it equal to 0. So you end up with x equaling plus or minus 6 as my critical points. All right, now that I've got plus or minus 6, I can't use the negative, right? Negative 6, I got to throw it out because it's not in the domain. Not in domain. So I can only test 0, 6, and the square root of 108. Those are the 3 things I need to test. And where do I test them? In my volume equation, right? X squared h. Because I am trying to, well, really, you're going to end up using this one. Let's put it right here, right? Because we've simplified it. So that's what I want to test it into to find my minimum value. All right, so now let's see. When I put in 0, obviously I get 0. So 0, 0. Okay? Then I put in 6. I'll get 6, comma 108. And then I try the square root of 108. And I'll get the square root of 108, comma 0. This produced the maximum volume. At x equals 6, the volume equaled 108. So this was this is what I needed to solve for the x. So the dimensions are 6 by 6, so 6 feet by 6 feet by. I can plug it back in here to solve for the h right here. Let me show you right here. Okay, I can plug it right back in here to solve for the h, and I've already done that for you, and the h comes out to be 3. And it's actually inches, 3 right there, 6 by 6 by 3. All right, let's move on to the second problem. Okay, so here's what I want you to do. I want you to fast forward the second problem, do all the other problems, then come back and watch me do the second one, because this second one's a little bit harder. So for number 2, it says which points on y equals 4 minus x squared are closest to 0, 2. So if I plot this real fast, and I'm going to do this on the side over here, oops, and I've got this parabola. It's an upside down parabola, and it crosses up here at 4, right? And I've got my point 0, 1, 2 right there, 3, 4. I want to know the points that are closest. So basically, I'm looking for that perpendicular distance and that perpendicular distance. Since it's symmetrical, if I find one right here, x comma y, the other one will obviously be negative x comma y. All right, since it's symmetrical. How do I find from 0, 2 to xy? Well, I need the distance formula. So let's go ahead and use our distance formula. The distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. So I'm finding the closest distance. So I want to minimize this distance, right? The closest means I want to minimize it. So that's my optimization problem, to minimize that distance. Well, let's put in the values we know. The distance equals, so I'm going to substitute values in and then minimize that distance. So this will be x minus 0 squared plus, and then this will be y minus 2 squared, right? Because this was the point right here, was the point 0, comma 2. And when I clean this up, I'll get the square root of x squared plus y minus 2 squared. All right, but I don't want to keep the y minus 2 because I've got two variables. Remember I said you always want to try to make this into one variable. So what I already know what y is right here. Y equals 4 minus x squared. So that means I can put y in right there. So I will substitute my y in. So that'll be x squared plus, and that'll be 4 minus x squared minus 2 squared. I substituted in. Let's clean this up. I'll get the distance equals the square root of x to the 4th minus 3x squared plus 4. Okay, now before I minimize it, I need to find the possible domain for this. Well, my domain, I can't choose anything that would give me a negative under the square root. So if I set this equal to 0, you will see that this graphs like this. So it's always above the axes. So basically, whatever value of x I choose, my y is always going to be positive. So the domain is all real numbers. So it doesn't matter at this point. I'm not really going to have endpoints that I need to worry about. All right, so now let's take a look. How am I going to take the derivative of this? Well, I can say this equals to the 1/2 power, but I can also do a shortcut. And here's my shortcut. Since the domain is all reals, all I really need to do is focus, and if I make f of x equal to x to the 4th minus 3x squared plus 4, if I try to minimize this, then the square root will also be minimized as well. If you don't want to do that, and if that bothers you, just take the derivative of this thing right here. Okay, take the derivative of that and minimize that. You'll get the same answer in the end. So it doesn't matter. I can just go ahead, because I'm solving for x. As long as I minimize this inner function, I'm going to end up minimizing that square root part of it. So let's go ahead. I'm going to do it with that shortcut way. And I will take the derivative here, and I'll get 4x cubed minus 6x, and then it goes away. It becomes 0. So I want to set this equal to 0, find my critical points, and I end up with 0 equaling 2x times 2x squared minus 3. So I get x equals 0, and then plus or minus root 3 over 2. Okay, so you need to test 0 and plus or minus root 3 over 2. And guess what? You get root 3 over 2. 0 won't work, right? 0 is going to, it's not going to work out that way. You know, just by looking at it, if x is 0, you get 2. You're right there. So it's going to end up being at plus or minus root 3 over 2 And then the y value, when I plug it in, I'm going to save you that time, becomes 5 over 2. So all I did was minimize this function right here, okay? And you didn't have to do it that way. You could have done this one right here and taken the derivative of that. You'll get the same answer in the end. All right, let's take a look at number 3 now. Number 3 says 4 feet of wires to be used to form a square and a circle. So we got to form a square and a circle with 4 feet of wire. Right here, let's use a different color. So I've got my square, I've got my circle, and I've got 4 feet of wire to form a square and a circle. How much of the wire should be used for the square, and how much should be used for the circle to enclose the maximum total area? So I need to maximize an area using a circle and square. And let me make a note of something that this problem didn't say. You can use it all in one. You don't have to use it in both. In other words, I can make one big square and I can make one big circle. So that's a situation we need to examine as well. All right, so I have 4 feet of wire. So let's take a look at what we can do with this 4 feet of wire. The area of a square, if I call this x, this is x squared. So the area here is x squared. For the circle, if I call this r, the area is pi r squared. So the total area, right, will be my square plus my circle. Oops, it's just pi r squared. I don't know why I put a 4 there. Okay, pi r squared. Now, the perimeters, if I take a look at those, the perimeter over here is 4x. Over here, which is the circumference, is 2 pi r. So the total perimeter is 4 that I can use, 4 feet of wire that goes around here and here, total 4. So when I add those up, I get 4 equaling 4x plus 2 pi r. So I want to solve for a variable and plug it in to the area equation. I would recommend solving for r in this situation. I just think it's going to end up being a little bit easier. How do you know? You sometimes it's just trial and error. I'm going to tell you for this one that it's r. You could have solved for the other one, and when I put it in, it may work a little bit different, but I think in this case we'll just go ahead and do it this way. So I'm going to solve for r, so this becomes 4 minus x divided by 2 pi, and that's what r is. Oops, equals r. So let's just do that. Okay, and now I'm going to put it in my area equation. So this becomes x squared plus pi times 4 minus 4x over 2 pi squared. Okay, let's clean this up a little bit. The area ends up being x squared plus, well, this comes out to be 4 pi squared on the bottom, so I get one of these pi's going with that, and I have that 4 on the bottom. So the top I'll just leave as 4 minus 4x squared. On the bottom, I'll put this as 4 pi. And obviously, at this point, you can't take a 4, because this is squared right here, right? You can't just take a 4 out. So we're going to leave it like this. I can try to FOIL the top out, but we're going to leave it like this for now. So I want to maximize the area. So what I'm going to do is I want to take the derivative here, right? dA dx, you can write it as a prime. It's fine. And when I do that, I'll get over here 2x plus, now remember this is 1/4 pi, 1 over 4 pi, and that's a constant. So if I multiply that through, I'll get 1 over 2 pi times this 4 minus 4x to the first power times negative 4. Okay, so cleaning this up, that reduces out to give me negative 2. So I'll have 2x plus, and now I can distribute a little bit. I got 1 over pi, and I'm going to just distribute it to this part. So that'll give me negative 4 plus, negative 8 plus my 8x. I could try to clean this up a little bit more, because remember I got to set this equal to 0. Before we do that, let's go back over here. I forgot to tell you, what would be the domain for this? What would be the domain? Well, if I chose, remember I'm using x here, I could choose x from 0, right? I can say there's nothing in the circle or the square and it's all in the circle. Or I could choose all the way up to 1. That would give me a perimeter of 4. So that's my domain for this one. I could choose x, a value of x from 0 all the way out to 1. If I choose 1, that means it's all in the square, nothing in the circle. Okay, so now let's finish this up over here. So 2x, and if I go ahead and this is going to be negative 8 over pi, and this will be plus 8x over pi equals 0. So I'll get 2x plus 8x over pi equaling negative, or now it'll be positive 8 over pi. So if I can multiply everything by pi, and I'll get, or actually let's just take out an x here. Okay, let's take out an x, and I'm left with 2 plus 8 over pi equals 8 over pi. And cleaning this up, x will be 8. There is another way to do this. You could have found a common denominator up at the top. In fact, in my notes, I did it that way, but here we're just going to go like this. Okay, so over here you end up with this complex fraction, and all of this will end up reducing into 4 plus pi over 4. Okay, I'll just go ahead and do that for you guys right now. Okay, so x ends up being approximately 0.56. So that's my critical point. So now I need to test 0, 0.56, and 1. So at x equals 0, I get an area of 1.273. At x equals 0.56, I get an area of 0.56. At x equals 1, I get an area of 1. Well, since I want to maximize this, that would mean I want to choose x is 0. So if x is 0, that means it's all in the circle. So choose x equals 0. It's all in the circle. There's your value. And that would be how to maximize it. Okay, so we're moving on now to what's number 6 here, because 4 and 5, maybe I might do them in class, or we'll just go ahead and skip them because they're way on the difficult level and something that they probably won't put on the AP test. But 6 is something they could possibly put on the AP test, so let's do that one. Over here it says an open-top box is made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending the sides up. How large should the squares be to make the box hold as much as possible? We're trying to maximize a box. And here's what we got. We have cutting out congruent squares of length x. So we've got a tin sheet, right, like this. And I'm going to cut out x's out of each corner. So I'm going to erase this and show you what's left when I cut out x's out of each corner. So if let me remove this. And then here's what will be left if I cut out x's out of each corner. I will have something that looks like this, right? Because I cut out these congruent x's, these congruent squares out of each corner. And what I'll end up with, it says it's 20 by 25. So if this is 20 all the way like this, right? And this is 25 all the way like that. And I know that this is x by x. Well, the length of this piece will be 20 minus 2x. And the length of this piece will be 25 minus 2x. So I fold it up, and I will get this box type shape when I do fold them together and fold the corners up, and I make that box. And this piece will be 25 minus 2x. This will be 20 minus 2x. And this height right there will be the x. So if we want to find how much it can hold, we are looking at the volume. And the volume is going to be the area of the base times the volume will be the length, the width, and the height multiplied all together, right? You can say the area of the base times the height. That's what I was going to say. So this will be 25 minus 2x times 20 minus 2x times my x. What I'm going to do at this point is let's determine the domain. All right, so for this, the domain, I can go from 0. So the domain, I can go from x equals 0. I can go all the way out to, well, I can't choose the one that's 25 because that would be too big. So I'd have to choose this value right in here. What would make this 0? This one would end up being too big, right? Because then it would already be negative in here. So if I chose x as being 10, that's the maximum I can go. Remember, if I went like 11, I start getting a negative in here. Over here, this one goes all the way out to 12.5. So I need the smaller of the two. That's why I'm choosing this one, and x would be 10. Well, if x is greater than 10, then I start getting negative values, and I can't have a negative value. Why? Because we don't want the negative volume. So the domain is from 0 to 10. So those are the endpoints that I need to test. Now, I'm going to tell you something. This is much easier right here to take the derivative of if you first FOIL this whole thing out, and I've already done that for you. 4x cubed minus 90x squared plus 500x. I FOILed it out. So now we can take the derivative of this because we want to try to maximize it, right? So taking the derivative of this will yield 12x squared minus 180x plus 500. Set this equal to 0. And now we're going to have to use the quadratic formula on this because I don't think it factors. And I will get x equaling, let's take a look here, 11.31 and 3.6811. 3.6811, sorry, 6.3811. So 11.31 and 3.6811. Well, guess what we have to do with this 11? We throw it out because it's not in our domain. I'll get negative values. So what do I have to test? We need to test. So this is my critical point, and you can put it on here, and you can put 3.6811. And you can put it here, and you'll see that this goes from positive to negative, so it will create a maximum, right? It'll create a relative maximum if you wanted to test it on V prime. I'm just saying that. But we already know that we're looking for these critical points, and we're trying to find the absolutes. So over here, I need to test 0, 3.6811, and what was the last value over here was 10. Those were the endpoints of my domain. Now look, obviously if I put 0 in here, I'm going to get 0 volume. Obviously if I put 10 in here, I'm going to get 0 volume. But this, when you test it, will end up yielding the maximum. And so the maximum will be V of 3.6811, right? And this will give me a maximum value of 820.53, and this is cubic inches. So at x equals 3.6811, you get a maximum volume right there. Okay? Looking at the next one, it says a liquid form of penicillin. I'm going to change my pen color here again. Manufactured by a pharmaceutical firm is sold in bulk at a price of $200 per unit. If the total production cost in dollars for X units, C of X equals 500,000 plus 80X plus 0.03X squared, and the production capacity of the firm is at most 30,000 units in a specified time, that should say time, how many units of penicillin must be manufactured and sold in that time to maximize the profit? So this is a profit revenue problem. So remember what profit is. Profit is the revenue minus the cost. Okay? So that's what we have to try to maximize is the profit. Well, what's our cost? This is our cost. So our profit, and what's our revenue going to be? Well, our revenue is going to be whatever we sell. In this case, it's these penicillins, and it's $200 per unit. So we know that our, before I do the profit, let me write this as the revenue. This is $200 per unit, okay? And my cost over here is going to be, this is C of X, and that should be R of X, 500,000 plus 80X plus 0.003X squared. So my profit in terms of X will be my revenue X minus my cost, which is 500,000 plus 80X plus 0.003X squared. Okay, so that is my profit equation. If I clean this up a little bit, profit is going to end up being negative 500,000 plus 120X and then minus 0.003X squared. Okay, we want to try to maximize this, but first let's determine the domain. What's the domain going to be? Well, I can make a maximum of 30,000 units. I can make none, or I can go all the way up to 30,000 units. That's my domain. So P prime over here, as we maximize it, that'll go away. I'll get 120 minus 0.006x, right? So solving this, set this equal to 0, I get x equals 20,000 as my critical point. So what do I test? I need to test 0, 20,000, and 30,000, because that's how far out I can go. Okay, so I need to test these 3 points. All right, if I put in 30,000, if I put in 0, obviously I will get 0. I'll lose money, right? I'll lose money. I won't have any profit. And if I put in 20,000, I'll get a profit right here. So this will be negative, so don't even worry about it. I'll get a profit of 700,000. And then if I put 30,000 in, I'll save you guys the time, and it's not going to end up being any greater than that. So this ends up being the maximum right here. So at 20,000 units is where I will reach my maximum profit. I tested the 0, I got negative. I tested the 30,000, I just didn't do the work for you guys, but if you put in 30,000 over here, okay, you won't get $700,000. You'll get something less than that. So this is $700,000. That ends up being our maximum profit. All right, let's take a look at this last one here. It says an offshore oil well located at a point W that is 5 kilometers from the closest point A on a straight shoreline. Oil is piped from W to a shore point B that is 8 kilometers from A. By piping it on a straight line under the water from W to some shore point P between A and B, and then onto B via pipeline across the shoreline. If the cost of laying the pipe is $1 million per kilometer under the water and $500,000 over land, where should point P be located so to minimize the cost of laying the pipe? Okay, so let me redraw it here since we had to change pages. Let me redraw it. Here's that point W, right? And here is where the water is, right along here. This is the water. So all of this is water, and you want to know, right, where to put point P. Let's do it in red. Where to put point P so that when you add up the cost of laying the pipe this way and the cost of laying the pipe that way, you get a minimum value for the cost. So I have my options of putting point P wherever I want. I could put it right here and then go underwater right here and all across the land right there. I can go all the way across, all underwater to point B. So those are the two extremes I have. All under here, then all this way, or all the way like that. Or find a balance point in between that will minimize that cost. So let's go ahead and set the cost structure up for this. What I'm going to do is, since I know that this is 8 kilometers across. If I call this piece x, this piece will be 8 minus x. Okay? So here's what I need to do. I need to add up both the situations. But assuming point P is somewhere here, you could put it right here. You'll get pretty much the same values. You could put it right here, but you'll get pretty much the same values. But I'm going to put it here so I could develop some sort of equation. Over here, for this, I will get the square root of x squared plus 5 squared. Okay? So that's what this distance will be. And if x is 0, it's obviously just going to be 5. Right? If x is 0, then it's obviously just going to be 5. So this is the distance underwater. This is the distance over the land. There's a reason why I picked this as the x, because if I would have put the 8 minus x here, then this becomes a pretty nasty equation right there. Okay? So now, we need underwater and over the land. Well, the distance underwater is the square root of x squared plus 5 squared. And what would give me the cost here? Well, let's do the land. The land is going to be 8 minus x. Okay, so now the cost of this will be 1 million, so I'm just going to write 1 million times this root x squared plus 5 squared, and I'm just going to change this to be 25 at this point, plus half a million, and I'm just going to keep it as 1.5 so I don't have to deal with all those zeros, and just know that I'm doing everything in terms of millions of dollars of 8 minus x. All right, so those are my two cost structures. What about the domain? Well, I can choose the domain. I can choose x being 0 all the way out to x being 8, right? So the domain can be from x equals 0, where it would be at this point, all the way out to x equals 8, where it would be at that point. So the domain is from 0 to 8. So those are the endpoints I have to test. So the cost in respect to x will be the square root of x squared plus 25 plus 1/2 times this will be 4 minus 1/2 x. So I've went ahead and reduced that down. So now let's take the derivative, and we're going to set this equal to 0. So the derivative of this will be 1/2 times x squared plus 25 times 2x, right? And since it's 1/2 over 2x, I'm going to clean this up for you guys. If you guys need to pause this and verify it, go ahead and pause and verify, right? Because it'll be to the negative 1/2 power. Then the 4 will go away, and this will be minus 1/2. And that equals 0 because I need to find my critical points. At this point, I can solve it. And to solve this, I'm going to bring the 1/2 over x squared plus 25 equals positive 1/2. I'm going to cross multiply. So I will cross multiply here, and I'll get 2x equals the square root of x squared plus 25. I will square both sides, so 4x squared equals x squared plus 25. 3x squared minus the 25 equals 0. Right? I brought everything over. So then I can't really solve it this way. We'll just solve it back the other way because it doesn't factor. So over here, 3x squared equals 25. I should have just left it like that. So x will be plus or minus 25, the square root of 25 thirds, right? Which will give me plus or minus 5 over root 3. Well, I got to throw out the negative. So here are my critical points. I got to throw out this negative 5 over 3 because it's not the negative one, right, in the domain. So my critical point is only going to be the 5 over the square root 3. So here's what I need to test. I need to test 0. I need to test 5 over root 3. And I need to test 8. All right. At 0, I will get a value of 9 million. At 8, I will get a value of 9.433981 million. And at this point right here, when I test it, remember, when I test this, I'm putting this back into my original cost equation right here, right? I'm putting it back into my total cost equation. So when I test 5 over root 3, I will get 8.330127. So this is my absolute minimum value. So the least cost will be at x equals, and this is going to be 5 over the square root of 3, and this cost will equal $8,330,127. That will be the least cost. All right, we will stop this problem. Thanks for watching. Hit that like and subscribe button. I'll do a couple more examples in class. I'm also going to have you do one. But hit that like and subscribe button, and I'll see you guys in the next video.